We looked at 3 examples of effective field theories. We didn't do a generic analysis, so one was QED, second was what? Was Second was Fermi theory, I think. Did we do Fermi theory? No. What was the second one? Seesaw mechanism. Leaky cup theory. And QCD. What is the third one? But K0, QCD, yeah. So today what we will try to do is systematically construct one particular effective field theory which could be sensitive to physics beyond standard model. So along the way, I'll tell you the rules of constructing the effective field theories. I'll tell you the, okay. Yeah, right. Okay, I'll again go back to K0 bar oscillations. Okay, and then I'll tell you again essentially. Okay, I'll do it more systematic manner essentially. Okay, so let's do K0 bar again. So K0 bar is essentially oscillations of K0 which contains ds bar to K0 has a strangeness +1, say for example, or -1. You take one of them. K0 bar will contain +1. If you take K0 to be strangeness +1, K0 bar will contain -1 essentially. So it contains at least one S quark. Whether S you want to define strangeness as -1 or +1 is your choice. Okay, let's take one particular definition and let's take ds is a bound state. Okay, mesons are made up of d and s bar. Okay, they are made up of d and s bar. So in this case, the K0, if I define K0 as strangeness +1, okay, S is equal to -1. Okay, strangeness K. Now this has two diagrams. Where S bar converts into an S and D converts to a D bar. Okay, I am explicitly writing, but normally you would express it from the sign of the arrows essentially. D converts into a D, S bar. So both of them have charge -1/3. So K0 has total charge 0. Okay, now these oscillations happen because of short distance effects. Short distance effects, because at the quark level, what is happening is W bosons are exchanged, and along with it, there is a Jim mechanism which is happening essentially. So the gym mechanism tells you that there is a non-zero CK matrix at these vertices, okay, at these vertices, which also cause CP violation, but later on we'll see essentially, which also leads to epsilon k and also the oscillations, the mass difference between these two. Because of the existence of the mass difference, there is a variation. The other diagram, oscillations, would be just interchange these two essentially. Now, how will you deal this process in an effective field theory? How will you deal this process? So there are two steps in this. There are mainly two steps. One, you compute this at the quark level. You compute this entire process at the quark level essentially. Because you know the physics is inside the quark level. Then you go to the long distance effects, which are essentially mapping these quark states into a meson state. Into a meson state essentially. Okay. So at the effective theory, if you are living with, so the degrees of freedom are say D and S. These are the only degrees of freedom at the effective field theory. What are the mass scales essentially? The mass scale, relevant mass scale in the theory is again set by the long distance particle, which is K0. Okay, because your experiment is done at a K0 mass scale. Okay, so the relevant mass scale now at the mass scale of K0, you don't know what this thing is. You don't know what this thing is. This is the interpretation you are giving in a higher theory at the weak scale. Okay, this is a theory. This entire thing, what you are saying, this is my standard model calculation. But there is no standard model at the weak scale. Okay, so this is called weak scale effective. Sometimes it's also called both are same. LEFT or WEFT are same. Okay. Now at that scale, I'll tell you how to get this. At that scale, there is no Higgs boson, there is no W boson, there is no top quark. Only masses which are available are essentially first two generation particles. Third generation also you can integrate out in principle. Okay. At that scale, below you can integrate top quark definitely. If you want, you can also integrate the bottom quark. Anyway, this effective field theory will not work for bottom quark because you need something else. Okay. Imagine that you integrated out top and bottom. So what are the quarks you are left with? You are left with UD, maybe C. Let's integrate C also. Okay, and CS. So C also can be integrated out, UD and S. And what are the leptons you are left with? Neutrino, electron, muon neutrino. C is integrated out, tau is also gone. So these are the only leptons. These are the only quarks here. Now you have the degrees of freedom. Now you ask the question, what are the symmetries I have in the theory? Okay. QCD. Okay. Then QED. Now, if you want to connect it with standard model, you can also put in Fermi theory. But otherwise, there's nothing. Now, if you want to connect it with saying that this entire oscillation phenomena is coming because of standard model, but not some other effects, it is coming because of the Jim mechanism in standard model, then you can connect it, put also Fermi theory. Okay. So I'll put a double slash. So while comparing with when you want to compute the SM prediction, you need to match with Fermi theory. If you don't want to, if you want to just match it with the experiment, okay, you don't need to worry about Fermi theory at all. If you are just saying that these are the operators which are causing something with my Fermi with my quarks, and then I map it with the kaons, and it's leading to this one. Okay, in that case, I don't even have to worry about Fermi theory. If you are just mapping with experiments. Now, when you are mapping with Fermi theory or really the standard model, you have to worry about left and right of the fermions operators you are writing down, because Fermi theory only standard model Fermi theory matching is only for left operators. Right operators don't have. But if you are just matching with experiment and you don't care whether standard model is the cause behind it or not, there is a CKM matrix, or these all, if you want to match it with CKM, match. Then you can write directly these operators, all possible operators. Now, because we are dealing with K0, not K plus, U quark doesn't play a role. Okay, we are not looking at any semi-leptonic decays or anything. Okay, or leptonic decays of K long or something, KL to mu E or something like that. We are not looking at those kind of decays, so the leptons will not play a role. So the only relevant degrees of freedom for this particular process are these two. Because what we are looking at is K0 amplitude bunch of operators, K0 H effective or L effective, whatever you want to call it. Okay, in this operator, now if you take another process, say for example K long H effective, it's a different effective, say so mu or mu E or whatever you want, looking at flavor, then you are worried about purely leptonic. Or then if you are looking at KL, it will be a different, another different operator K plus. Then, or if you are looking at K plus, okay, 3 pion decays or something. So for each process, you have to write a separate effective operator, so say Hamiltonian. Separate effective Hamiltonian or effective Lagrangian, whatever you want to write. process essentially. Yeah. You are not worried about writing the full thing, but you can write the full thing actually. You can write the full thing. Okay. So when you do this, so let's worry about this particular process. So you have operators. So you want to call it as C1. Okay. The first set of operators in H effective. What you'd write H effective is nothing but a series of operators C1 to C9. Okay, C1 to C9. Now C1 to C9 are very easy to write down because the only operators are essentially D and S. So what kind of operators you can write down with D and S fields? You know from bilinear covariance. You know the scalar. You know the pseudoscalar. Okay. You know the meaning vector, actual vector. Everything you can write. So you write down all possible operators because they are all allowed by symmetry. So what are the symmetries? Because only QCD and QED. You don't even care for the present. Let's be a devil's advocate and we say that I don't know if there is a standard model behind. I don't know if there is CKM behind or something. Okay, which is causing this. I'll write down all possible operators in this particular fashion. Okay, so I'll then say C2 by lambda square. Okay, all possible operators I'll write down. Okay, then I also have the dipole operator and the chromomagnetic operator. Here you have to worry about the alpha and beta indices. Okay, because these are color indices which also have to connect with the G mean of the color indices. Okay, so you can write all possible such operators. Okay, you can write you start with dimension 6 operators, but you can also write the a dipole operator, a chromomagnetic, photomagnetic operator, chromomagnetic operator, and so on. Now immediately you will see that the chromomagnetic operators will not play any role because there is no photon or a gluon outside, or there is no two other quarks. It's not a decay process. So the chromomagnetic operators will not contribute. You can write a most general effective operator, effective Hamiltonian with all possible operators involving only D and S fields. But you will know immediately what will be the relevant operators here. The relevant operators would be C2 with the couplings of vector like because we know the diagram already, inside diagram already because we know the standard model. Okay, if you don't know it, I'll try to fit everything. I try to fit with everything with all possible operators. Of course, you saw that. Now, what you do, you write down all these operators. Now, you evaluate this effective Hamiltonian, putting each operator at a time. Putting this each operator at a time. So, I'll put in C1 by lambda square. Now this is a matrix element which I have to evaluate. This matrix element I can evaluate using lattice or chiral PT. But I already know the short distance effect from C1. If I know the short distance effect in standard model, I can calculate it. I know what is the value of C1. So I know all the kinematic factors and everything. Okay. What I don't know is just the overall factor, which is Fk. Okay. Okay. So this I will use it from lattice. So C1 I know what is this. C2 I will try to put, and I will say that this should correspond in the process with the initial state this, final state that. It may go to 0. C2 may go to non-zero. C3 will definitely go to 0. Or C7 will definitely go to 0. So it won't contribute. C8 definitely go to 0. So I'll ask the questions if there are any parity violation here. The operators are parity violating or strangeness conserving, Lorentz invariance, all this I impose on when I am evaluating these amplitudes. Okay, and from that I know what are these amplitudes, which ones of these operators contribute significantly to this particular process. Okay. Now if I want to calculate the standard model operator prediction, then now here what is the scale? This scale can be anything. I don't know what the scale is. It can be top mass, it can be standard model mass, it can be anything. I am sitting at a scale very close to the scale of the K base, K0. But instead, if I want to calculate what is this operator or what is this thing within the standard model, what is the prediction of K0, K0 bar within the standard model? Now, up to here is fine, right? Because I am just using QCD and QED. I am not using any standard model already. If I want to instead predict what is the thing, I calculate this particular C1 and C2 and so on. So I try to match it with the standard model calculation. I try to calculate this, do diagrams. Then I do a matching. At what scale I should match? And at what order I should match? So this diagram is only valid, so you can forget about the top, but the top plays a very important role. If there is no top, this gym mechanism will not work. Okay, right? So let's imagine that I do the matching. So, but this operators are defined at a scale lambda, which is close to say mk. Okay, now but from mk to v, I have to run them up. So I need RG equations for each of these Wilson coefficients. Okay, so RG equations. So I wrote there are 9 such things. They could be 11. So they are typically say 9 operators. Most dominant, most general cases of operators there are about 9. So I need these operators to run from mk to all the way close to v, wave of the sun. How do I run them? So I need to run right Ti there will be something which are called anomalous dimensions, which determine the RG equations of these Wilson coefficients. Now, so far I have not done anything with the standard model. You see, I have not done anything with the standard model. So these Gamma ij is not diagonal. Okay, gamma ij is not diagonal, so it will mix different operators. Okay, it will mix different operators. So what you say that what at weak scale you define C1 will be equivalent to C1 plus some 10 times or 0.01 times C3 at the high scale. Okay, so this is called the anomalous dimension matrix. So it's non-diagonal matrix. So this is called anomalous dimension matrix. It is non-diagonal and leads to operator mixing. Operator mixing has different meaning also. For the present, we'll just call it as this as operator mixing. Okay, the operator which is, if I start with one operator at weak scale, at the high scale it will equal to some linear combination of 2-3 operators. Okay, because of this RG running. Now whether it is significant or not depends on the model. In some cases it's not significant, in some cases it could be different. Now I am sitting here. Okay, I am sitting here close to the standard model scale. I calculate these diagrams. Then I'll make an identification C1 or C1, or let's call C1 by lambda 2 square, which is equivalent to G2 square by NW square, some VIC JK VIJK star JK star the CKM elements. Okay, this kind of identification you will make on the Wilson coefficient by the lambda square. Okay, so this is gives you your what is the Wilson, each Wilson coefficient it can disentangle and calculate and put here essentially. And with this you have the standard model prediction, or you can start the other way around. You can do it here and then match it down essentially. Now this is 3-level matching roughly, and 1-loop RG equations. You can do it much more. You can do 2-loop RG for this and 1-loop level matching here. Okay. This relation by calculating these diagrams explicitly in standard model and then matching with these operators at the standard model scale, I am getting this. These are the RG equations. These are called anomalous. It's also called anomalous dimension, but these are RG equations written. So you have this Hamiltonian, right? Now you take this Hamiltonian and you can write the how this Hamiltonian runs with energy. So you can renormalize this Hamiltonian at 2 scales and see the matching between say how do you match the Hamiltonian behaves at 2 different scales. Okay, assuming that you know one scale, if you know you renormalize it at 2 different scales, and the relation of the renormalization between the 2 different scales gives you the RG equations. So you can derive for a given Hamiltonian, assuming that it's a renormalized theory, you can derive the RG equation. So you can actually derive this RG equation. Okay, and you use these RG equations to calculate this. Now you say that there is an anomaly now. Okay, now this part will, now you bring it here, you match it with the standard model calculation. This is a loop calculation. You do this loop, you compute this box, it gives you some number. This number you match the amplitude at the weak at the high scale. Yeah, they're in bound state. here, here, here we assume, because it's short distance effect, you assume that it is factorizable, that the long distance and short distance effects are factorized. They are bound states only at the weak scale. Below lambda QCD. Okay. Pardon? Yes, exactly. So what we can do, so now you start, okay, let me write them here. You can do it diagrammatic approach, or actually this is the main contribution comes from QCD. Okay. Otherwise also you can actually, what is this thing. So let's take this operator. This is just nothing but this operator. Okay. This is this operator. So this operator, so all of them have the same Feynman diagram. So except that you have to change the indices and everything. Now this will have some gluon index A alpha, beta, gamma. I don't know. Essentially some gluon index such that it all sums over. Okay, alpha. Now you can worry about matching the gluon indices here, all possibilities essentially. Okay, that I didn't talk about, but you can always match the gluon index. Now imagine that there is a gluon here. The dominant contributions are coming from QCD corrections. Okay, the QCD corrections, imagine that there is a gluon affected here and absorbed here. Okay, or reverse. Okay, and so on, so there will be 4 such diagrams. Now this diagram, it turns out it's actually not very difficult to calculate. Okay, it turns out that the gluon corrections, QCD corrections, can be easily calculated. Okay, by just, they all factorize out by the central operator, and they can be absorbed in the running of the alpha essentially. They can be absorbed like running of the alpha. Okay, so if you have, so this diagram will be equivalent to, by this diagram times some alpha by 16 pi square by some constant, let me call it C, times some log factor. Okay, which corresponds the difference between the scales. So the QCD corrections are much simple to calculate at least one level. Okay, so this will end up being some constant times alpha s. Okay, alpha s tilde is alpha s by 16 pi square. That is the standard notation. Okay, you can write it as alpha s by 16 pi square times say mk by q square. Mk square by q square. So this calculation is, as far as QCD is concerned, is simpler for the QCD running. What happens if we have non-QCD running also? Then the things become complicated. The RG equations have to be explicitly computed. Okay, but this case QCD corrections are roughly, you can always take the operator and multiply with the alpha s times the scales and everything by this particular constant. You have to evaluate this constant, but it's also can be evaluated. Done. Clever. Okay. So now you can ask the question, why there will be one operator related to another operator essentially. Okay. So, but then This gluon, look here, gluon is massless. It will be there. You cannot integrate it out. Yeah, it will be there. You also have other diagrams, right? Settings here itself. Hit here, here, here. So QCD is always there here. We assumed in, yeah, QCD is always there. And also you can do the same thing with QED. You can also put a photon, but they are much smaller. So you don't care about the QED corrections. Yeah. Alpha S. Of course, because uh, these are this. There are a bunch of C equations, right? These are a bunch of C equations. But then these gammas will contain alphas. So you have to run the alphas also, right? Essentially. Right, essentially. They'll contain numbers, but also there'll be a gamma for alpha S, there'll be a gamma for alpha 2, there'll be a gamma for alpha electromagnetic. So that is taken out. Okay, for each gamma there will be a separate thing. For each force or for each interaction there is a separate. Yeah. So yeah. So these are your now with this you integrate this, calculate this, get this matching. Now how do you get the matching? Because I know the high energy theory, which is the standard model, calculate it, the process in the high energy theory, then match it with the operators in the low energy effective field theory. So you are matching it with SM and LEFT. Okay, you are matching in SM and LEFT or weak scale effective field theory. Okay, so then you will get your standard model prediction. There you will get your standard model prediction. Now this standard model prediction will not have, it's a complete trigonometric result theory. LEFT is not, it has to be done order by order carefully. Okay, it has non-reducible operators, but once you match it, okay, you get your LEFT operators or weak scale effective field theory operators, match them with the standard model with the corresponding explicit couplings of the CKM, everything, you get them here, and then you can calculate and put this back into this, put it now the question you raised, because they are their bound states now, put these operators, run them down to the weak scale, after the matching put them back here, calculate in putting FK and all these chiral PT operators and everything, and make the prediction. So this is the prediction of the standard model, you say, with an error bars. The error bars dominantly come here, dominantly come in the long distance effects. The short distance you can compute explicitly, okay, accurately. The typical hadronic process will have an error bar of 20%. Okay, this that's a very large number, whereas flare process have experimental accuracy is around 2 to 3%, and if they are semi-leptonic or leptonic, the error bar is 1% or something. So to know these things very well on a lattice is so important. That's the reason why every 2-3 years we have a new anomaly in B physics or K physics, because these error bars are extremely large. Now there could be some process which you wouldn't expect to happen in standard model. So some process which are expected, so if you do some angular correlations, and these angular correlations are very well predicted in the standard model because it's a parity violating theory. So you expect what is the forward backward asymmetry and those kind of things. Angular correlations, you know what they are. So if a theory has right-handed correctness, so it won't have, there won't be forward backward asymmetry. There will be much more symmetric. So there are processes, say B to K L plus L minus, say for example, another low energy process. There you can take angular correlations of the lepton, okay, leptonic pairs, and so on. So, and these can be well measured in Bell or Barber or one of these experiments. They can be used to test the standard model, and they can be used to test the CP. In addition to that, you can also test CP violation. Okay. So there is this channel called B to gypsy K short, which is supposed to be the golden channel to measure time dependent CP violation in standard model, which was measured. Okay. So similarly, for each such process you have, you can test the standard model very accurately in the flavor process using effective field theory approach. And whenever there is an anomaly, that means it's not matching with the standard model, you do what? You replicate this bunch of operators, call them as standard model operators, plus write a bunch of unknown operators, the same thing, but you call them as C tilde. Okay, so you say that these are all standard model operators, and then you write another bunch of operators. In principle, it's not needed. Okay, so this is with the matching of this, plus you also write another bunch of operators which you call BSM. So C tilde C1 by lambda square, the same thing, and then see how much is the value, or C tilde, what is the standard model contribution, and the difference can be fit with this bunch of new operators. That's the game of B physics, because you will invariably find some anomaly, okay, because of the large error bars. Okay, you keep playing this in terms of operator, but there are of course a lot of deep physics within it. Around epsilon, it's epsilon 4s. Its root s is, it's a symmetric machine, you know that, right? It's not a symmetric machine. Both the beams don't have the same energy. Okay, so that it is asymmetric, and it's yeah. So and it is in such a way that it has a resonance at epsilon 4s. Epsilon 4s. So BB bar bound state and its variance. Okay, higher values of that is about 5 point something, around 5 GeV, 5 point something. Bell 2 may be slightly higher actually. The Bell is around that 5 point something. 10 GeV. No, it didn't go that far. Maybe, yeah, maybe that. It is at a higher resonance of epsilon. Not really that high. Not up to 10 GeV. I don't remember. Maybe, I don't know. So it will be around 5 to 7, not more than that actually. Okay. Yeah. So, yeah. You want to 7? Yeah. So this point is clear. This point is okay. Yeah. Yeah. So, yeah, this is completely different from what I wanted to talk today. Actually, yeah. Okay. Yeah. But anyway, it's good. Yeah. Because of the arginine, because the diagrams, the loops, purely because of the loops. Right. In most cases, the mixing is very, very small. What we observed is in most cases, um, it is in some only in those cases when you are having purely hadronic states, like for example, the mixing is very large. So if you are looking at a process which is a decay, say for example, um, some such process, say for example, B going to gypsy K short. Gypsy, you know, CC bar bond state essentially. K short is K on, K long and K short. No, there are two things, DS bar. Now this is a process in which a beam is on. Let's see if we can draw this essentially. So W am I drawing it correctly? B to C. Ah, okay. I think the diagram is correct. Okay. Now this is a process. This is what's happening. So B converts into a C through some CKM VCB. Okay, and then you have W going into C and an S. Okay, another CKM here. Okay, and then there is a D of the D, which is of the B. Okay, it's the same thing. It remains as it is. So this is K short. This is gypsy, and this is now this is a purely hadronic process. Now there could be, now you write down the operators. What are the bonds, meaning degrees of freedom here? So what will be the degrees of freedom? Up to B. B, D, S, C, everything essentially, okay? So let's assume these are your degrees of freedom. These are the only things which are. Now then, could there be some gluon contributions which could lead to this decay? This is a weak process, right? Can you draw a diagram with a gluon? B meson decon gluon. So when you write down these operators, what happens is, so you have gluons which can come from this side and mix it with this operator. So you an operator which is written with BD or BC, okay, can have, say, this gluon can sit here, can sit with the other operator. You can write an operator with BC, but this gluon can be emitted in the BC operator, can end up with CS operator. So the CS operator is mixed with BC operator. So similarly, you can remove, put another gluon here, it will go somewhere there. Okay, if you write bunch of operators BC, so because you had to write every the effective Hamiltonian will contain all the 4 fields. But a gluon can start with one of the operators which you are saying, say if you write one operator only here, because it's a product of 2 operators, right? Effective Hamiltonian will have 2 operators. So one of them land up here and another will land up here. Now that could be equivalent to another operator. That's the point dimension. That could be equivalent to another operator completely. That could be equivalent to another operator completely. So this operator, which you have written as product of BC and CS bar, would be equivalent to Pierce identity of another operator because of the change of exchange of a gluon or exchange of currents. Just by radiative corrections, it can get mixed essentially. Okay, so this becomes quite cumbersome because it's, and they are not small. Unlike the case we were dealing with where QED corrections and Fermi theory corrections are typically small, the operator product expansion mixing is typically small. You are saying something. No, this is a this is a golden channel because it's a tree level channel. Okay, but there could be a loop actually. There could be there is a loop also. There could be a gluonic loop. There could be loop corrections also. Yeah. No, gamma ij independent of these loops. No, gamma ij is coming. See, gamma ij is not derived using this. Gamma ij is derived from these loops. Okay, right. Gamma j has, you don't even touch up to here. Okay, yeah, gypsy. Why this channel is very popular is because this is called the golden channel actually, the CP violation and everything. Golden channel. So there are all these names. So when you calculate this, the calculation is easier. There is a factorization theorem and everything. But when you write an anomalous matrix, because you have gluon mixing, there could be operator mixing also. At the weak scale, it's very simple to actually do it. But this is a process in which strong interactions can play a role, very big role, because all the 3 are strongly interacting. The short distance effect may be a weak effect, but all the 3 are strongly interacting particles, so you can have long range effects also between them. So some gluon going around and going very far and touching the other one. So all of this is happening within a Fermi. The only thing which doesn't have a range is weak interaction. Strong interaction has a range of 1 Fermi. By definition, it has gluon is photon. Gluonic photon is massless, so it's a long range interaction, but except for the boundary of 1 Fermi. So, whereas weak interaction is point-like. It is a really short distance interaction. It just happens at the same space-time point. That's it. I am unable to hear you. Yeah. Yeah. In principle, you should write down all operators, but you see when you are doing the calculation, you see which are relevant operators, and you can neglect the rest of them. You don't have to write operators which don't contribute to the process at all. For example, K0 K0 bar doesn't make any sense to add a chromomagnetic operator or dipole operator or so on. So, okay. So depending on the process. So suppose if we take a process like processes involving decays, which are this is a decay. The process, say for example, which are semi-leptonic. Say B2K L plus L minus. This will be complicated because they'll have penguins, they'll have boxes. Here and instead of when you have a penguin, you also contribute to the final state. So you'll have a diagram like this. This is one possibility, and the same thing can also happen with this. Something like this. Okay, so these, because you have two sets of diagrams, then things are much more complicated. Essentially, here you have boxes, you have penguins, and so on. And so it depends on the process. In this process, typically boxes are suppressed, but still you have to include them because there could be some kinematic regions where they could play a role, and in some cases there could be accidental cancellations in the penguins, and the boxes could become dominant some regions of the parameter space. So all these interplays will happen. So it is safe to consider all the operators, derive the RGEs and do them, but such a thorough job is important only for very well measured things. For typical order of magnitude calculations, you can just take the dominant operators. Okay. Now there are codes like Flavio is there essentially, which does. So he's an expert. You can talk to him. Which uses LEFT and uses all the data, and you can do global analysis. Now what happens is, suppose if you write an effective Hamiltonian, this operator can contribute in several processes. So it may be weakly constrained in one process, but very strongly constrained in another process. So chromomagnetic operator, say for example, chromomagnetic operator, dipole operator may be strongly constrained, may be weakly constrained, say in delta mk or bb bar with the mass difference or something, but may be very strongly constrained in a decay, like B to KL plus L minus or B to S gamma or something. So you have to take this bunch of operators and do a global analysis. Okay, so sticking to one process will not be good when you are analyzing the data. So you have to worry about all possible outcomes, all possible decays which have been measured, all possible process which have been, not just decays. There are not many scatterings, but anyway, the on process, say oscillations or CP violation, you have to measure. And the same operator may be less constrained in some place, but be more constrained in some other place. So you cannot say that, okay, I am only considering this particular operator. and so this operator is less constrained by this particular process, so I can work with take this value as much as it wants. That won't work. Okay, so same number of degrees of freedom, same symmetries, but there could be several processes which lead to the same constraints on the effective operator Hamilton. That's the reason why they do a global analysis, and these codes like I don't know, Flavio, Wilson, all these things help you in doing that. Wilson does the RG running and everything, matching, and Flavio does the matching, so on so forth. Okay. Yeah. What time is it now? 12:40. Okay. Now, one interesting thing is, these guys got awards also. Manohar and company, Jenkins. They have written RG equations, derived the RG equation for all possible LEFT operators. Okay, all possible LEFT operators, they have written the RG equations up to the weak scale. Okay, Jenkins and Manohar. Okay, so these you don't have to re-derive them. You don't have to worry about re-deriving them. They are there. You can just use them. Because at the low energy level, there is no BSM or SM or anything. These are your operators. You can write them as separately as BSM and SM, but in general they are known and the RG effects are same. Okay, and that's it. There are no new interactions, nothing else. So everything is known. So it's you can derive them, and it has been derived, and we know you can use them. So, so I want to do SMEFT today, but before being, because we introduced already LEFT, I'll derive what are the different types of effective field theories within the standard model and so on. So I'll define these EFTs in terms of degrees of freedom plus the symmetries. Okay. So one of the most popular ones is called standard model effective field theory. This is the one which is used to study BSM physics. Okay. This contains all SM particles. Okay. This is called GSM. I'll write one more thing here which it makes important sense. Higgs is linearly realized under the symmetry. Okay, so that means Higgs goes as Higgs is linearly realized. That means under the symmetry it's not non-linearly realized. I'll tell the difference a bit later. This is called same set of particles. So typically Higgs is like a Goldstone boson. Okay, Higgs is non-linearly realized under the gauge symmetry. So if so, or H by V, something like this. So the Higgs goes as an expansion of e power times some coupling or some coupling constant by H by V, essentially it's some xi or something, some coupling. So what does nonlinear? It's like a nonlinear realization. That means it is almost like a Goldstone boson. So this is for composite Higgs models and so on. So for most of the composite Higgs. Now the question comes, which is bigger? Whether this is bigger or this is bigger in terms of the field space it covers, whether HEFT is bigger or SMEFT is bigger. Okay, in terms of all possible theory models, say for example, if you have some sort of a theory space, if we can imagine, so it turns out HEFT is bigger. HEFT is much bigger. And there will be a smaller role of SMEFT. So for all possible theory models or something you can consider of BSM or whatever possibilities, HEFT is much bigger than the same energy scale. Energy scale is the same. SMEFT is a subset of HEFT. One can consider SMEFT as a subset of HEFT. One can consider, but exact showing is not easy. Technically, it's very hard. So there are a lot of debates, lot of papers, everything written on it. Okay. Other thing which I'll mention is also that most of these cases, what we use is we reduce the number of operators by going on shell. We use the equations of motions to remove some of the operators. So that means you are putting everything on shell. They are all on shell. So whether these on shell methods are covering the entire region or not is one more question. Okay, if the on shell methods, so some of the fields could be off shell, right? Like in the loops and everything. Now we are insisting by using equations of motion, all the fields are on shell. Okay, and you are writing the bunch of operators. Does it make sense that if some fields of the standard models also could be off shell? Okay, will you get a much larger range? Okay, so we are using on shell methods and everything, then okay, because it's by definition it's on shell, because we are using in the WhatsApp basis. In the WhatsApp basis, we remove a bunch of operators, okay, by using the equations of motion. Okay, so there are these questions whether SMEFT is larger or HEFT is larger. Okay, but this is a schematic picture. One should remember that HEFT is much larger, but technically whether you can show it or not, it's a different question essentially. Okay, and whether if there is a parameter somewhere here, whether which it falls into, if you measure some measurement, whether it falls into HEFT or whether it falls to SMEFT is very hard to tell. So how do you distinguish between these two is also very hard to say. Okay, so which regions will be, so if you ask what is a particle which is only here, what is a model or which is an operator which is only here, which is not there, is very hard to tell. What is the region of the parameter space also. At some higher order in SMEFT, that operator can come here. At least experimentally we cannot tell right now. We are not in such sensitive ways. And the reason is purely because of the Higgs. Okay, I'll tell you essentially. But once we construct the SMEFT, you'll see why. SMEFT is nothing but taking a standard model and multiplying each operator with H dagger H. So you get SMEFT essentially some 2500 operators or something. Okay. So this is SMEFT. Then there is the low energy effective. So all SM particles minus all SM particles, this set minus top Higgs W Z, that's it. So whatever is left, you are left with gluon, photon, okay, as the two gauge bosons and rest of the fermions. So minus Higgs, you integrate out top Higgs, W and Z. So that is the LEFT, which is the operators which we have seen for flavor process, axion physics. So for all this, for axions or anything, what we typically use is LEFT. You don't need the full SMEFT. Or sometimes it's also called weak scale effective. Now the theory is here. What are the symmetries here? The symmetries are essentially SU3 G Fermi. Okay. But the symmetries are only these two. Okay, Fermi theory is not a symmetric thing. It doesn't impose anything. So this I'll just leave it, because if you want to put the Fermi theory, it will be useful for those processes where it contributes. Okay, for those processes where it contributes. So these are the main effective field theories relevant to us within the BSM classes of model. Okay, so what you do, if you have a BSM model sitting somewhere here, you match it with SMEFT or HEFT, then match it again, run it down, okay, and see what are the relevant operators in LEFT, and then do the experimental matching. If it is a low scale, so something which happens in B factories or something. Okay, if you are dealing with light dark matter or something. Okay, so these are the various kind of effective field theories relevant here. Then there are other bunch of effective field theories which are not, which we won't talk about at all. Essentially, there is something called SCET, soft collinear effective field theory. There is something called heavy quark effective field theory. Okay, then there are various QCDs, NRQCD, non-relativistic effective field theories. So of this, there is something called NRQCD, NRQED, more relevant for nuclear physics or dark baryons or something like that, for example. Heavy quark effective field theory is more for B physics. Collinear effects in colliders. Okay, so there are all this bunch of effective field theories which are used. In principle, every theory is an effective field theory. Okay, so you should view every theory as an effective. That's the basic summarize of Weinberg. Essentially, that every theory should be viewed as only as an effective field theory, following Wilson. Essentially, okay, following Wilson. But then there are problems actually. As usual, like there could be non-decoupling effects and stuff like that, which we'll deal. Okay. Okay. So I'll stop here, and I'll do on Thursday what I can.